Dear students, today we will learn performance analysis of solar cell. So, before we start our today's discussion, let us summarize what we have discussed in the last class. So, we have discussed classification of semiconductors, doping, Fermi energy level, p-n junction, drift current and diffusion current, and generations of solar PV materials. Of course, we have studied the working principle of a solar cell. So, with this background, we will now move to today's discussion on performance characteristics of PV cells, which includes IV characteristics, equivalent circuit diagram of a solar cell, both in actual and theoretical, as well as our conventional equivalent circuit diagram, then theoretical maximum power, how to calculate theoretical maximum power, then effect of insolation and temperature on IV characteristics, and finally cell efficiency and band gap will be discussed. The solar cell characteristics at room temperature when a junction not illuminated. So, how it will look like? It will be something like this, okay? And mathematically it can be represented by I is equal to I naught multiplied by exponential of V by Vt minus 1. This is the expression we can use for a dark current, okay? So, this I naught is nothing but reverse saturation current, which is dependent on temperature. Of course, it tells about the diffusion of minority charge carrier from neutral section to the diffusion layer, okay? And this Vt is something called voltage equivalent temperature, okay? And mathematically it can be represented by K into T divided by E. What is K? Is a Boltzmann constant. So, already we have discussed this Boltzmann constant in the last class. Its value is about 1.381 into 10 to the power of minus 23 joule per Kelvin. And charge of an electron is about 1.602 into 10 to the power of minus 19 joule per voltage. So, this Vt value is about 26.0 millivolt at 20 degree C. So, its value is 26.0 millivolt at 20 degree C, okay, at room temperature. Okay. Now, we will discuss what happens when p-n junction is illuminated or light source is applied. Okay. So, what will happen? The shape of this IV characteristics will change. Okay. So, it will go downward and then you can see how the shapes has been changed. So, these two figure is for two different light level. Okay. So, this is ISC for one light level, this is ISC for one light level. This ISC is short circuited current. Okay. So, we will define how this can be investigated. Okay. So, mathematically when the p-n junction is illuminated, we can express something like this: I is equal to minus ISC plus this part. Okay. So, this ISC what we have got after exposing to the light, right. So, that has to be added. Okay. Since it is a fourth quadrant, so this will be minus ISC. Okay. So, when the junction is short circuited at its terminal, this V is 0, this voltage is 0 and a finite current will be I is equal to ISC, which will flow through this junction from positive terminal to the negative terminal. Okay. So, this current is known as short circuited current or short circuit current, right. Now, if we provide some kind of voltage source to this p-n junction and the positive side is connected to p side and negative will be a negative n type, then what will happen? This voltage will start rising from 0 and a little increase. Okay. So, this should also sense, and finally what happens at certain voltage this current will be 0. Okay, this current will be 0. So these voltages are known as VOC for light source 1 and VOC for light source 2. Okay. So this VOC at which current is 0 is known as the open circuit voltage. Okay. So if we substitute I is 0 in this equation and when we simplify, then what we will get? An expression for calculation of VOC. So VOC is nothing but Vt multiplied by ln of ISC by I naught plus 1. Okay. So we can calculate the value of VOC by knowing these parameters. Okay. So at room temperature, normally if we consider a silicon solar cells, then ISC is about 2 ampere and I naught is about 1 nanoampere. Okay. Hence, if we substitute this value here and we use Boltzmann constant and charge of an electron, then VOC is found to be about 0.55 volt, okay, for a single crystal silicon solar cells. Okay. So what we have understood from here is that when light source is provided to a PN junction, that can be considered as an energy source. Okay. So now we can understand we can generate energy out of this junction. Okay. Now let us learn the IV characteristics, okay, and in the convention what we normally use. So for energy source, by convention the current coming out of positive terminal is considered as positive. Okay. Mathematically, the characteristics of solar cell may be written as I is equal to ISC minus I naught exponential V by Vt minus 1. This is the expression normally we use. Okay. So if I have to draw IV characteristics, then we need to follow some kind of instrument, IV tracer, or maybe we can make our own arrangement to know how this voltage and current is related. Okay. So if I am interested to generate this IV characteristics curve, then what we will use? IV tracer we can use, and we can get different values of current at different voltage. So these are the points. So if we join this point, so this will be something like this, and finally it will be joining at 0.6. If we say open circuit voltage is 0.6. Okay. So how it varies? Initially this current will be almost constant, and then sharply it is decreases to 0. Okay. So if we consider this is x axis, this is y axis. Okay. So intersection of x axis will give VOC and intersection of y axis will give ISC. Okay. So these ISCs are very sensitive to solar insolation, but not VOC much. Okay. Also, if we can generate this IV, we can also generate PV curve, power versus voltage curve. So if we vary power with respect to voltage, then what will happen? We can join those points, okay, and we will get a maximum point, and then it will decrease to this 0 power. Okay. So in every cases what we will have this kind of plot, and it will pass to a maximum and then it will reduce to 0. So this maximum point is very, very important. So if we can operate our system at this maximum point, then we are expected to have higher power conversion, and of course we will get higher solar energy conversion efficiency. Okay. Now combining these two, we can generate this kind of plot. Okay. This is the IV part, okay, and variation of power with respect to voltage is given here, right. And if we identify this is the maximum voltage and this is the maximum current, okay, so we can form this kind of rectangle. Okay. So this is the area under the curve. So area will be Im into Vm, right. So this closeness of the characteristics to the rectangular shape is the measure of the quality of the cell, which is very, very important. Okay. So this will give rise to a parameter called fill factor. Okay. which is nothing but mathematically Vm multiplied by Im divided by VOC into ISC. Okay? So, this Vm is the maximum voltage, Im is the maximum current, and VOC is the open circuit voltage, ISC is the short circuit current. Okay? So, value of this ISC varies from 0.5 to 0.83 for is crystalline silicon solar cells. Okay? So, an ideal cell would have a perfect rectangular characteristics, that we should remember. Okay? Now, come back to this figure. Here what is shown, two cells are connected in series, okay, for this case, and two cells are connected in parallel. So, if we are connecting two cells in series, then what will happen? Of course, voltage will rise, and if we are interested about this maximum voltage, so this maybe we can put Vm1 and this maybe we can put Vm2. So, and this may be Im1 and this may be Im2. So, here voltage will be at this point Vm1 plus Vm2, and if we are interested about power, that has to be multiplied by Im1. Okay? And in this case what will happen? We will have Vm1 multiplied by Im1 plus Im2, right. So, that way we can calculate for different cells, right. Also, what we can define the instantaneous efficiency. If I am interested to know the maximum instantaneous efficiency of a solar cell, that can also be calculated by using this simple expression. This Im multiplied by Vm to the solar power, means amount of solar radiation received by the solar cell. Okay? Since we already know the expression for FF, we can relate instantaneous efficiency with respect to fill factor. Okay? So, if we relate this, then our final expression will be something like eta I is equal to fill factor multiplied by IOC into VOC into ISC divided by IT into AC. So, this AC is the cell area and IT is the amount of solar radiation falling on the particular cell. Okay? So, once we know these parameters, we can calculate eta I or instantaneous efficiency. Okay? So, here point is, if any system operates less than this power point or maximum power point, then we are losing the efficiency. So, our attempt is to operate the system at maximum power point. Okay. Now, let us do some kind of calculations to know fill factor, okay, of a solar cell. So, if these informations are given to us like VOC, ISC, Vm, Im, then straight away you can calculate what will be the fill factor of a solar cell, right. So, here based on our calculation it is found to be 0.34, which is not so good, okay, but still what we have shown, this is the way how to calculate fill factor. Okay. Now, if I am interested to calculate the maximum power and electrical efficiency of a solar cell at an intensity of 200 watt per meter square, how to do that? If these values are given, VOC is given, ISC is given, Vm or V maximum is given, I maximum is given, and area of the solar cell is given as 4 centimeter square. So, straight away you can calculate P max is I max into V max. So, this will be 0.84 milliwatt, and instantaneous efficiency by using the expression what is discussed in the last slides. So, we can get an efficiency of 2.7%, which is very, very less. Here of course, we have used positive sign, because conceptually we need to use positive sign. Okay. So, we can have this instantaneous efficiency as 2.7%, which is very, very less. So, this is an demonstration how this can be calculated. Okay. Now, let us learn the equivalent diagram. So, in order to understand the characteristics of a solar cell, we need to plot this equivalent circuit diagram. Of course, this is an actual equivalent circuit diagram. Okay. So, what are the components involved in this diagram? We will have a current source, okay, and we will have junction, PN junction, okay, or say diode, and we will have shunt resistance, then series resistance, and this is load resistance, right. So, current source supplies current which is equal to ISC, okay, and Ij is the amount of current which flows through this PN junction, okay, and ISH is the amount of current which flows through this shunt resistance, and I is flowing through this RS. Okay. RS is the series resistance, right. So, this is an actual equivalent circuit diagram. Okay. This short circuited current is not equal to the light generated current, but it is less by shunt resistance or shunt current through RHH and internal voltage drop RS. Okay. So, normally in practical situation when we do the calculations, so these are neglected. Okay. It is assumed that this is RH is very very high and RS is very very low. So, distribution of power is very very less when current flows through this series resistance. Okay. So, in these situations, the mathematically this characteristics can be written something like this: IL minus I naught of this expression minus V plus IR S divided by RHH. Okay. So, these are the components which are added. Okay. RS is also here. Okay. So, values of this RHH, okay, for a high quality 1 square inch solar silicon cells is about 200 ohm to 300 ohm, and RS is about 0.05 ohm to 0.1 ohm. From here you can see the how this resistance varies in case of shunt resistance and series resistance. Okay. So, here point is this IL, okay, so cannot be directly equal to ISC, right. So, it involves lot of losses if we connect this RHH and RS. Okay. So, normally resistance is very very high in case of shunt resistance, and here series resistance, no, resistance is not much. That is why the energy distribution is not much. Okay. So, let us see what happens in case of ideal equivalent circuit diagram. So, we can omit these two components, shunt resistance and series resistance. Okay. So, our considerations are shunt resistance is infinite and series resistance is 0. Okay. So, here only current source we have, then we have Ij is the junction current and I is the current flowing through this load resistance having voltage drop of V. Okay. So, now our intention is to calculate this P max. Okay. So, in order to calculate P max, that is the maximum power which can be provided by a cell, we need to calculate what is Im and what is Vm. Okay. Let us see how this can be calculated. So, this load current at fixed values of temperature and solar radiation can be related with voltage. Okay. So, this I is related with voltage with this expression which is already defined, right. So, I is equal to ISC minus I naught exponential of EV by KT minus 1. Okay. So, as we know, for an open circuit voltage I is 0, so V is equal to VOC, right. So, if we substitute this in equation 1, then our equation will be something like this. Okay. So, if we simplify it, then we will have this expression, and once we have this expression, if we take ln in both the sides, then what we will have, we can calculate what is VOC, which is nothing but KT by E multiplied by ln of ISC by I naught plus 1. Okay. So, by using this expression, we can calculate what is the open circuit voltage. Okay. The power P from a PV cell can be calculated by using P is equal to I into V, which is known to us. Okay. So, if we substitute this I from equation 1, then our equation will look like this. Okay. So, this equation may be equation 3. So, as you can understand, when we have discussed in IV and PV characteristic curves, so combined we can have this kind of plots, okay, not exactly. So, we will have maximum point somewhere here, okay. So, this is the maximum point, okay. So, at this point what happens, dV by dP, sorry dP by dV is equal to 0, this gradient will be 0, okay. Okay, if P is here and then V is here, of course dP by dV will be 0 at this point, okay. So, this is the point. So, under that conditions what we will get, that we will call P max, okay. If we know these values, then we can calculate P max, right. So, if we use the expression what is developed in the last slides, and if we differentiate with respect to voltage, so our equation will be something like this, and if we multiply with voltage and then differentiate with respect to voltage, and then finally expression will be something like this, okay. So, here what we can do, this V can be replaced by Vm, because at this point or here, okay, for IV. So, if you actually here this will be I and P may be in the secondary line P, okay. So, this may be, okay, Im, this may be Vm, this may be Im, okay. So, once we know Vm and Im, so of course we can calculate what is Pm, right. So, at these conditions here, okay, where dP by dV is 0, then what we will have, we can have this expression for Vm. So, by using this expression we can calculate what will be the value of Vm once we know Isc and I naught, okay. Since these values are known, okay, these values are known, okay, and we can have Vm, okay. And this load current Im corresponding to maximum power can be determined by substituting this equation 1 in equation 5, okay. So, by using this and simplifying this, so we can have this expression, and let us continue with the next slides. And by using equation 4, then we will have this kind of expressions, and if we multiply this equation, both sides of this equation with I naught, then what we will have is a maximum current. So, expression for maximum current is something like this, okay. And once we know this Im, then finally we can calculate what is be the maximum power, okay. So, maximum power is nothing but multiplication of Im into Vm. So, Im is known here and Vm already we know the expression. So, by using this expression we can calculate what is Pm. Of course, while calculating Pm we need to do trial and error, okay. So, that way we can calculate the maximum power to be delivered by a solar cell, okay. So far what we have learned is the open circuit voltage, okay. What is open circuit voltage, what is short circuit current, what is maximum power point, okay, what is fill factor, what is efficiency, okay. These 5 parameters we have studied, and we understand now what are those parameters and how this can be calculated, okay. Now, again extension of this performance characteristics, as you can understand, when solar radiation intensity increases, so Isc value increases, okay. So, as you can see here, so as Isc increases, again no Im and Vm also increases, okay. So, here this is for one intensity and this is for another intensity. So, of course, this will be at a higher intensity than this one. So, you can see this rise in Isc when the solar radiation increases, okay. But variation of VOC is not much even though solar intensity increases, right. And this Isc is dependent on size of the solar cells and then solar insolation, that we should keep in mind, okay. If we increase the size of the solar cell, then it is expected to get higher Isc values, and also if we increase the solar irradiation, then Isc value can be increased, okay. But this VOC, the open circuit voltage, depends on the type of cell and type of cell or cell material, okay. So, this is fixed for a particular solar cells, okay. this solar cell output power increases with solar radiation, right. The change in short circuit current are essentially proportional to the change in solar radiation. Okay. However, the change in voltage are comparatively less, what we have shown in the figure, right. Also, in the very beginning of this class, we have demonstrated how this eta max can be calculated. So, this expression already familiar to you. So, this with respect to FF, how it will look like, and if we do not have FF, only IM and VM, then also you can calculate eta max. Okay. So, already you know what is IT is the incident solar flux, and AC is the area of the solar cell. Okay. So, this maximum conversion efficiency of a solar cell is given by the ratio of maximum useful power to the incident solar radiation, right. So, this you should keep in mind. So, for an efficient cell, it is desirable to have high values of fill factor, okay, as you can see here, right. So, if we can get high values of fill factor and then higher values of ISC and higher values of VOC, of course, we can maximize our efficiency. Okay. So, now interestingly, you can notice that high values of short circuit current are obtained with low band gap material, okay, while these high values of open circuit voltage and fill factors are possible with high band gap material. Okay. So, then we have to make some kind of compromise. Okay. Otherwise, we can see how this efficiencies varies with band gap. Okay. Then we can pick the best band gap for maximum energy conversion. That also we will discuss in the coming slides. Okay. So, in order to understand the concept what we have discussed, so let us take an example of something like this. The dark current density of a solar cell at 38 degrees C. As I said, this dark current density is always dependent on temperature. Okay. So, it is very, very sensitive to the temperature. Okay. And the short circuit current density is 235 ampere per meter square. Now, we need to calculate the voltage and current density that maximize the power of the cell. Okay. That means, we need to calculate IM and VM. Then second case, what we need to calculate? What would be the corresponding maximum power output per unit cell area? Okay. That means, power density you need to calculate and then corresponding conversion efficiency. If the global radiation incident on the cell is given as 865 watt per meter square. Okay. Also, in the third case, we need to calculate the cell area if the output power is given as 45 watt. Okay. What is given here is I naught by AC is given as 4.3 into 10 to the power of minus 8 ampere per meter square. Okay. And ISC by AC is given as 235 ampere per meter square, and temperature, since we need to convert this centigrade to Kelvin, then we have to add 273. So, it will be 311 Kelvin. Okay. So, this our relationships are valid only when we take T is in Kelvin or temperature is in Kelvin. Okay. So, already we have those expressions already derived. ISC by I naught is exponential of EV naught by KT minus 1. Okay. By using this expression, what we can calculate is the VOC. Okay. So, open circuit voltage we can calculate. So, we substitute these values and taking ln in the both sides, and then finally, what we can have is VOC is 0.601 volt. Okay. Also, we know this expression. In order to calculate VM, we need to use this expression, right. Then on substitution of those given data, then we can develop this expression, right. So, we cannot solve these expressions straight away. So, we need to solve it by trial and error. Okay. So, we need some kind of prior knowledge about VM, because already you know VOC is 0.601. So, VM has to be less than 0.601. Okay. That way we can decide what will be the probable values of Vm. Maybe we can start with 0.5, then maybe 0.55, okay. Then we can see which one is closer to these values. Then finally we can decide what will be the exact values of Vm which satisfies this equation. So once this equation is satisfied with this assumed Vm, then we can calculate what is Vm, okay. So this Vm will be 0.521 volt for this case, okay. Now once we know this, then we can calculate maximum current density, okay. So this expression we can use. So the kind of expression what we have used during derivations, there IC was not there, okay. So what we can do, we can take that expression. So that expression was Im is equal to EVm by kT, then we will have 1 plus EVm by kT, then I naught plus ISC. And if we divide this expression, this may be star expression, this star if we divide by AC, then what will be the expression is something like this, okay. So why we have done it? Because these values are given in terms of densities, okay. So that is why we have done it. So Im by Ic on substitution of these values, then what we will get is about 223.496 ampere per meter square, okay. So now what we can calculate is the maximum power. So Pm is equal to Im into Vm. So this will be the Pm, okay. Since we know this Im, okay, and this will be watt per meter square, since this Im is in watt per meter square, okay. So this is for maximum current density, okay. So Pm is Im into Vm. So finally what we will have, this is a maximum power per unit cell area. So this is the answer of question B, okay. And this is also part of answer B, okay. So finally that is maximum conversion efficiency. We know the equation Pm by I, because this Pm here is density. So I into A, okay, is taken care of this Pm. So that is how we can calculate I max. So it will be about 13.46%, okay. So if we need to find out AC or say cell area, how to do that? Let AC be the area of the cell, and we know this eta max, and P is given as 45, then we use this equation, and from that we can calculate what is AC or area of the solar cell, right. So this area of the solar cell we can calculate by using this procedure, okay. For this case it is about 0.3865 meter square, okay. So in this problem we have first calculated VOC, then we have calculated Vm, then we have calculated Im, then we have calculated Pm, then we have calculated eta max, and finally we have calculated eta c. So we have shown how these parameters can be calculated from a given data, okay. So this kind of exercise is very important to understand how these equations can be used for calculation of all those performance parameters, okay. Now let us learn the effect of solar cell temperature on solar cell efficiency, which is very important. A fraction of total solar radiation incident on a solar cell produces electricity, and remaining radiation is converted into thermal energy, okay. A part of the produced thermal energy raises the temperature of the solar cell, and the rest is dissipated from the top and bottom of the cell, right. The temperature of the cell determines the electrical performance of the cell, okay. So if we do the energy balance per unit area, so we can have this kind of equations, okay. Losses will be there, and then we have efficiency, and then amount of energy received by the system, okay. So what is tau? Transmissivity of the cover of the solar cell. then alpha is the absorptivity of the solar cell, then eta c is the electrical efficiency, right. And of course, UL is the overall loss coefficient, which includes top loss and bottom loss, right. Also, we will introduce one term called NOCT. So, in the back side of the PV module, normally you can see this NOCT is written, that is normal operating cell temperature, which is nothing but the temperature of the solar cell corresponding to 20 degrees C and 800 watt per meter square solar irradiance, and wind speed is 1 meter per second under no load condition. Okay. So, for no load condition, eta c will be 0, no electrical conversion will be there. Okay. So, this expression what we have discussed in the last slides, it reduces to something like this, and from here you can calculate what will be the cell temperature. Okay. So, expression of cell temperature will be something like this, right. This the electrical efficiency is a function of temperature. Okay. So, this electrical efficiency again related with this expression. So, what is eta naught is the electrical efficiency of the solar cell under standard test condition. So, what is under standard test condition? This solar radiation has to be at 1000 watt per meter square, then wind speed is 1 meter per second, okay, and AM 1.5. Okay. These are the minimum requirement for this standard test condition. And beta naught for silicon solar cell is about 0.0045 Kelvin inverse, okay, which is known as efficiency temperature coefficient. Okay. And already we have defined what is Tc, which is nothing but solar cell temperature. Okay. So, by using this we can calculate what will be the electrical efficiency of a solar cell, right. Now, let us learn how this efficiency of a solar module related with temperature. Okay. As temperature increases, what happens in both the cases for amorphous cell and crystalline cells, efficiency decreases. This decrease is more significant in case of crystalline solar cells. So, as you can see, its decrease is about 0.4 to 0.5% per degree rise in temperature, and for amorphous cell it is about 0.25% per degree rise in temperature. Okay. So, when the module temperature rises up, the efficiency decreases. Okay. So, we need to have some kind of cooling for improving the efficiency. So, normally natural coolings are preferred, but why this is happening? Okay. So, let us learn at fixed insolation, if temperature is increased, there is a marginal increase in the cell current, okay, but a significant reduction in the cell voltage. And second cause is an increase in temperature causes reduction in the band gap, which causes some increase in photogeneration rate and thus marginal increase in the current. Okay. The reverse saturation current, which was represented by I naught, increases rapidly with temperature. Okay. So, it was reported that the cell voltage decreases by 2.2 millivolt per degree increase in temperature. Okay. And also it is observed that lighter the silicon resistivity, more marked is the temperature effect. Okay. And last cause is fill factor also decreases with temperature. Okay. So, these are the causes why actually this with rise in temperature conversion efficiency decreases significantly. Now, here it shows the variation of insolation as insolation increases, how this characteristic curve changes. Okay. Also, this power versus voltage curve changes. Okay. We can see the shift of maximum power point if we trace it from here. Okay. And this plot shows the effect of variation of temperature on the characteristic of the solar cell. Okay. So, as temperature increases, this IMVM also decreases. Okay. So, this is very clear. So, this may be for one case, okay, and this may be for another second case, okay, and this is for at 25 degrees C and this is for at 60 degrees C. Okay. See how these changes are taking place. Okay. Now, let us see how this solar cell efficiency and band gap are related. Okay. So, here in this figure, two curves are considered. So, one curve is generated under a spectrum of AM 1.5 and another curve is generated under the spectrum of AM 0, which is extraterrestrial region. Okay. So, this curve 1 is extraterrestrial radiation is incident on the solar cell, and curve 2 incident global radiation to the AM 1.5 under a clear sky. Okay. And it is assumed that intensity of solar radiation is 1000 watt per meter square. Okay. So, if we plot it, then what we can get? So, this is for silicon and this is for gallium arsenide. Okay. So, if we see, as we understand, this eta max is related with fill factor, okay, then ISC, then VOC, then we have here is the IT into SC, right. So, this will be more, this will be good for high values of band gap and this will be for low values of band gap. Okay. So, what we can say, in this range solar cell efficiency is found to be high. Okay. And if we see this is about 1.1, okay, and this is about 1.7, close to 1.7. So, if we consider a band gap in between this range 1.1 to 1.7, it is expected that we will get higher conversion efficiencies. Of course, we can do lot of iterations by varying this band gap and we can optimize or we can maximize what will be the maximum efficiency of conversion. Okay. So, this table shows the variation of efficiency with different solar cell material. As you can see very precisely, this fill factor and efficiency, there is a relationship. See, when fill factor is more, efficiency is very high. Okay. So, fill factor is more, efficiency is high. Okay. So, this fill factor plays a very important role in enhancing the efficiency of a solar cell. And this table shows the efficiency values of some PV modules. Okay. So, this also quite clear. So, for silicon single crystal module, so we will have higher efficiency about 22.7 and the same time we will have higher fill factor. Okay. So, comparison can be seen. For multicrystalline it is about 15.3% efficiency and fill factor is about 17.6 and other two cells are also given here. Okay. So, what we can summarize in this talk, we have understood the performance characteristics of a solar cell and also we have studied how this fill factor can be calculated, ISC can be calculated, VOC can be calculated, IMVM and maximum efficiency can be calculated. And what is ISC, what is VOC, how this ISC and VOC are sensitive to solar insolation and size of the cells, that also we have discussed, and also we have derived to estimate the maximum power of a solar cell. Okay. Also we have studied the effect of variation of solar insolation and temperature on the characteristics of solar cell. Finally, we have studied solar cell efficiency and band gap. Hope you have enjoyed this lecture. Thank you very much for watching.